This is Matt Dean with A Plus College Ready, and today we're going to work some circuits practice problems. We're going to start off with a series circuit, and we're giving that the potential difference across the battery is 6 volts. So here's our battery. Resistor R1 has a resistance of 1 ohm, and resistor R2 has a resistance of 2 ohms. First of all, we want to find the total or the equivalent resistance. Since there's only one pathway for the current to flow through in a series circuit, you find the total resistance simply by adding up the resistance of each resistor. So in this case, 1 plus 2, we get an equivalent resistance of 3 ohms. To find the total current, we're going to use Ohm's law, which solved out for current is I equals V over R. So our V is our battery voltage or potential difference, 6 volts. We're going to divide that by our total resistance, which was 3 ohms. So 6 divided by 3, we end up with 2. Current is measured in amps or amperes, 2 amps. Now, since there's only one pathway in a series circuit, the current that leaves the battery has to go through R1, through R2, and then back to the other terminal of the battery. So in a series circuit, the current is constant. If 2 amps leave the battery, 2 amps go through both R1 and R2 and return to the battery. So that means this is 2 amps. This is also 2 amps. Next, we're asked to find the voltage drop across R1 and R2. They might also ask us for the potential difference across R1 and R2. To find that, we're going to use Ohm's law again. And we're going to say V equals I times R. That's just Ohm's law solved for voltage or potential. So we know the current through R1 is 2 amps. We know the resistance of R1 is 1 ohm. That means the voltage drop across that resistor is 2 volts. At R2, same idea. V equals I times R, 2 amps of current, but R2's resistance is 2 ohms, which means the voltage drop across R2 is going to be 4 volts. Next, we're asked to find the power dissipated at R1 and R2. There's a couple different ways you could do this one. The formula that most people are going to use is P equals V times I. You also might use P equals I squared times R. And that formula is derived from substituting Ohm's law into P equals VI. We're just going to use VI. So at resistor 1, we have a voltage of 2 volts. So V is going to be 2 volts. At resistor 1, we have a current of 2 amps. So 2 amps times 2 volts gives us power, and it's going to be 4. Power is measured in watts, so 4 watts. At resistor number 2, P equals VI. So at resistor 2, the voltage is 4 volts. The current is 2 amps. So 4 volts times 2 amps gives us 8 watts. All right, that's a basic series circuit. All right, so next we've got a multiple choice question. So here we have a series circuit. It's got 2 light bulbs, both of which have a resistance of 3 ohms. We want to know how much current flows through each bulb when the circuit is attached to a 12-volt battery. So the first thing that we need to do in a situation like this is find the equivalent or the total resistance. Remember, in series, you find that simply by adding together the resistance of each resistor. So we've got a total resistance of 6 ohms. To find current, we use Ohm's law. I equals V over R, which in this situation is the potential difference across the battery, 12 volts, divided by the total or equivalent resistance of 6 ohms. So we end up with a current of 2 amps. That's how much current comes out of the battery. Now remember, we think of current flowing, conventional current flowing from the positive terminal of the battery. There's only one way for it to go, so it's got to go up and through this bulb. It's got to go up and through this bulb, and then it's got to return to the negative portion of the battery. So if 2 amps come out, 2 amps have to go through this bulb. 2 amps also have to come through this bulb. 2 amps have to return to the negative terminal of the battery. So our answer on multiple choice question 1, 2 amps. All right, so multiple choice question 2 is the same circuit, same values. This time we want to know what is the potential difference across each bulb. We might also hear that called the voltage drop across each bulb. So again, to find the voltage drop, we already know that the current through each bulb is 2 amps, and we know that the resistance of each bulb is 3 ohms. So to find the voltage drop, V equals IR. That's just Ohm's law, solved for voltage. So at this bulb, the current is 2 amps. The resistance, 3 ohms. Multiply that together, we get a voltage drop of 6 volts. Now, we could calculate it for this other bulb. We get the same thing. It's important to note that in a series circuit, the voltage drop across all of your loads will add up to be the voltage drop across your battery. So 6 volts here plus 6 volts here is equal to the voltage drop across the battery of 12 volts. So our answer, C, 6 volts, is the potential difference or the voltage drop across each of our bulbs. All right, now we have a parallel circuit. And notice in a parallel circuit, there's at least 2 different paths that current can flow. When the current gets to this junction, it could go down this branch, or it could go down this branch. In this case, we have a battery voltage of 12 volts. The resistance of R1 is 6 ohms. And the resistance of R2 is 12 ohms. We're asked first to find the total or equivalent resistance. In parallel, you want to use the relationship that the total resistance 1 over the total resistance is equal to 1 over the first resistor plus 1 over the second, and so on. If we had third, it would be plus 1 over 3, and so on. So in this case, 1 over the total equals 1 over 6 plus 1 over 12. So you want to do basic fraction math here, get a common denominator. 1 over 6 is going to be equal to 2 over 12. We add those together. 1 over the total resistance is equal to 3 over 12. Now that's not the total resistance, that's 1 over the total resistance. So to solve for the total resistance, we need to flip both sides of this relationship. So RT is going to be equal to 12 over 3, which 12 over 3 is 4 ohms. So our total resistance, 4 ohms. Next, we want to find the total current. And again, when we're looking for total current, typically we're going to use Ohm's law to find that. Ohm's law solved for current is I equals V over R. So we'll take our battery voltage, 12 volts, divided by our equivalent resistance, 4 ohms, and we're going to end up with a current of 3 amps coming out of the battery. Next, we're asked to find the current through resistor 1 and resistor 2 and the voltage drop across resistor 1 and 2. Important thing to remember, voltage drop or voltage measures the amount of potential energy per unit of charge. If we have a truly parallel circuit, not a mixed circuit, the voltage drop across each branch is going to be equivalent to the voltage drop across the battery. Well, there's only one resistor on each of these 2 branches. That tells us that the voltage drop across the battery is equal to the voltage drop across here and the voltage drop across here. So our voltage drop across 1 is 12 volts. Our voltage drop across 2 is 12 volts. Now I did that because I really need the voltages to find the currents. To find the currents, again, I'm going to go back to Ohm's law, I equals V over R. At resistor 1, the voltage drop was 12 volts. At resistor 1, the resistance is 6 ohms. So 12 divided by 6, I get 2 amps of current going through resistor 1. At resistor 2, same relationship, I equals V over R. The voltage drop is 12 volts, but at resistor 2, the resistance is 12 ohms, which means the current going through resistor 2 is 1 amp. Notice that those 2 currents have to add together to be the total current coming out of the battery. Lastly, we're asked to find the power dissipated at R1 and R2. And remember, we can find that one of several ways. P equals VI or P equals I squared R. Let's, in this case, just use I squared R. Doesn't matter which one you use, you're going to get the same answer. So at resistor 1, P equals, the current through resistor 1 is 2 amps. So that's 2 amps squared times R. The resistance at R1 is 6 ohms. So 2 squared is 4. 4 times 6 is 24. And remember, power measured in watts. And then at number 2, P equals I squared R. So P equals, through number 2, we have 1 amp of current. So 1 amp squared times the resistance at number 2, which is 12 ohms. So 1 squared is 1 times 12. We get 12 watts of power being dissipated at resistor number 2. And that's a basic parallel circuit. Some important rules to think about. The current that goes through this branch plus the current that goes through this branch has to equal to the total current. As long as you have a straight up parallel circuit with only one resistor on each branch, the voltage drop across the battery is equal to the voltage drop across each of the 2 branches. All right, next we have a combination circuit. So this is sort of a series circuit and a parallel circuit merged into one. This time we have a battery voltage of 12 volts. Resistor number 1 has a resistance of 8 ohms. Resistor 2 has a resistance of 6 ohms. And resistor 3, 12 ohms. We want to find the following. It's always a good idea to find the resistance of the parallel portion of the circuit first. So let's find the resistance of just this part of the circuit. There's the parallel part. Remember, to find parallel resistance, it's 1 over the total. We'll call that RP for right now. Is equal to 1 over the first resistance plus 1 over the second resistance. So just like we did in the previous problem, 1/6 is 2/12. So we add those together. 1 over RP equals 3 over 12. We have to flip both sides of this relationship and get RP equals 12 over 3 or 4 ohms. So this is 4 ohms. Now, the easiest way to work this problem from here on out is to think of this circled part, the parallel part of my circuit, as one series resistor with an equivalent resistance of 4 ohms. So if we think of this now as a series circuit, to find the total resistance, we're going to take this resistor, 8, plus, again, we're thinking of this whole thing as one resistor of 4 ohms. 8 plus 4 is 12. Because remember, in a series circuit, you simply add together the resistances of each resistor to get the equivalent resistance. To find the total current, Ohm's law, I equals V over R. So we take our battery voltage, 12 volts, divide that by our equivalent resistance, 12 ohms, and we end up with a current coming out of the battery of 1 amp. Now, that current leaves the positive terminal of the battery, flowing this way, conventional current, gets to resistor 1. All of the current gets there because that resistor, R1, is in series with the battery. So if 1 amp come out of the battery, 1 amp has to go through R1. Now when the current gets to this point right here, it has to split. Some of it has to go through R2, and some of it has to go through R3. And we're going to have to figure out here in a second how that works. Maybe the easiest way to think about that for right now is that if we're thinking of this whole thing as one resistor, all of the current has to go through it, 1 amp. It has an equivalent resistance of 4 ohms, which means the voltage drop across this whole parallel circuit is 1 amp I times 4 ohms R. That tells us that the voltage drop across the parallel part of the circuit is 4 volts. Now that's across the whole parallel portion of the circuit. But remember, in parallel, each branch is going to have the same voltage drop. So if the whole thing has a voltage drop of 4 volts, the voltage drop across R2 is 4. The voltage drop across R3 is also 4. So let's record those. Now that we have those voltage drops, we can find the currents because we know that current I equals V, 4 volts for R2, over R for R2, which was 6 ohms. So we divide that out, 4 over 6, we end up with 2/3 or 0.67 as the current through R2. Through R3, same relationship. I is going to be equal to the voltage drop, 4 volts, divided by the resistance of R3, 12 ohms. So that's 1/3 or 0.33. And note that 0.67 plus 0.33 add up to be the total amount of current through the circuit, which is 1 amp. Now let's go ahead and find the voltage drop across R1. To do that, at R1, voltage drop is going to be equal to I times R. We have 1 amp of current going through R1, and the resistance of that resistor is 8 ohms. So the voltage drop across R1 is 8 volts. Now again, notice that the voltage drop across this resistor plus the voltage drop across this whole parallel part of the circuit, which we're thinking of as one series resistor, 8 plus 4 gives us the total drop across the battery, 12 volts. Final thing, we need to find the power dissipated at each resistor. This time let's just use P equals V times I. So P is going to be equal to, at resistor 1, the voltage drop at resistor 1 was 8 volts. The current through resistor 1 was 1 amp. So the power dissipated at resistor 1 is 8 watts. At resistor 2, same relationship. We're going to take the voltage drop across resistor 1, or 2 rather, 4 volts, times the current through resistor 2, 0.67. Multiply that out, and we end up with 2.68 watts dissipated at number 2. And then finally, the same relationship happens also at number 3 resistor. So the voltage drop across number 3 was 4 volts. The current through resistor 3 was 0.33 amps. So we multiply those together, and we end up with a power dissipation of 1.32 watts at resistor 3. So that's a combination circuit. You want to first find the parallel portion of the resistance. Think of that parallel part of the circuit as one series resistor, and then use series rules to work your way through the circuit. All right, so we're back to multiple choice question 3. In the circuit shown to the right, R3 has a resistance of 4 ohms. So this is 4 ohms. While the sum of the resistances of R1 and R2 is 12 ohms. So we don't know how much each resistor is, but we know the total resistance of this branch is 12 ohms. If 6 amps flow through R3, so we got 6 amps of current that go this way, we want to know how much current goes through this branch. Now at first you might think you need the voltage, the battery voltage, to figure that out, or the EMF. You don't. What you should realize is that the R1, R2 resistance, that branch resistance is 12. The resistance of branch R3 is only 4. So the resistance of this branch is 3 times the resistance of this branch. If the resistance is 3 times more, the current is going to be about 1/3 as much. So if 6 amps go through the R3 branch, only 1/3 of 6 amps, which would be 2 amps, go through the R1, R2 branch. So our answer, 2 amps. It's also important to note that if 2 amps go through R1, 2 amps also have to go through R2 because there's only one pathway through this branch. So this question would be no different if they had asked for the current through R2. It would still be 2 amps. All right, so same circuit we looked at in question 3. R3 is 4 ohms. The sum of the resistances of R1 and R2 are 12 ohms. But we now measure that R1 has a resistance of 2 ohms. Well, these two resistors, R1 and R2, are in series. Their sum of the resistances add up to be 12. This one's 2. That should tell you that this one has to be 10 ohms. Now it says we then move R2 to R3's position and R3 to R2's position. How does the total current through the battery change due to the swapping of the resistors' positions? All right, so first of all, let's figure out what the total resistance is as is. And the way we would do that, we're going to take 1 over the total resistance, and we're going to say 1 over, when we're using this formula, 1 over RT plus equals 1 over R1 plus 1 over R2 and so on. These should be branch resistances, the resistance of the whole branch. So 1 over RT is going to equal 1 over 12 plus 1 over 4. Get a common denominator of 12, so 1/4 is 3/12. So that's going to be equal to 4 over 12. Just like we did before, we have to flip this and this. So right now, the total resistance is 12 over 4, or 3 ohms. So that's before we change anything. We've got 3 ohms of total resistance. Now, it tells us that R2 and R3 essentially are going to get swapped. So we're going to take R3 and R2. So now this is now going to be R2, 10 ohms. This is going to be R3, 4 ohms. And let's go ahead and find out what's the resistance now. So it's going to be 1 over RT equals 1 over, in this case, the branch resistance is 6, 2 plus 4. And the branch resistance over here is 10. All right, we're going to get a common denominator of 60. We're going to add those together. So let's see, that's going to be 10 over 60 and 6 over 60. So that's going to add up to be 16 over 60 equal to 1 over RT. We're going to flip this and this over. RT is going to be equal to 60 over 16, which is about 3.75. So this is the total resistance of the circuit after we move the resistors. This is the total resistance before we move the resistors. So after we move the resistance is higher. We know that when there's more resistance, there's less current. Those two are inversely proportional. So if you look through our choices here, because we now have more resistance, we're going to have less current. The answer here is going to be C. The current is going to decrease because the total resistance increases when we move those resistors. All right, question 5 is the same circuit. This time we have different values though. R3 now has a resistance of 2 ohms. The sum of the resistances of R1 and R2 is 6 ohms. So this whole branch resistance is 6 ohms. If 3 amps flow through R3, how much current flows through the battery? So we're saying we get 3 amps of current going this way. So 3 amps of current go this way. Important thing to note is that, first of all, this branch resistance here is 3 times the resistance of this branch, which means that 1/3 as much current is going to go through the R1, R2 branch as goes through the R3 branch. So if 3 amps go through this branch, only 1 amp is going to go through this branch. Well, what that tells me is that if I have 3 amps going this way and 1 amp going this way, those two currents are going to come together right in here, and that's going to give me the total current going back to the battery, which is going to be the 3 amps here and the 1 amp here. A total of 4 amps come out of this battery. So our answer on this one is C, 4 amps. All right, so next multiple choice question. The table below shows the potential difference. Again, that's another term we might use for voltage drop. And the current for each circuit element in a circuit consists of a battery and 3 resistors. Which of the following diagrams could represent the circuit? So as we look through our table, what I'm hoping you note is that you have 4 amps coming out of the battery, and that the current through every circuit element is the same. I hope that clues you in that when you have a constant current throughout the whole circuit, that tends to be a characteristic of series circuits. Another thing that we want to think about is that in a series circuit, the voltage drop or the potential difference across each resistor, when they sum them up, that should add up to be the potential difference across the battery. So here we have 4 plus 6 plus 2. Those do add up to be 12, the potential difference across the battery. So I'm hoping that this shows you that the series we're looking for in this question is a series circuit. And if you look down here at the bottom, the only circuit that we have that's a series circuit is A. All right, number 7 looks almost just like number 6. The stem of the question is the same, but notice our table is very different, the values in our table. This time we have a total current coming out of the battery of 3 amps. 3 amps also go through the first resistor. But then through resistors 2 and 3, that current splits. If we look at the voltages, the voltage drop across resistor 1 is 3 ohms, but resistor 2 and 3 have an identical voltage drop. One thing that you should think about here, when you have identical voltage drops across resistors, that might be indicative that you're talking about a parallel portion of a circuit. Also notice that we have current splitting, and that those two currents that split add up to be the total amount of current. So I'm hoping that this clues you in that the answer we're looking for here is C. This is a combination circuit. 3 amps come out of the battery. They grow through resistor 1. They get here to this junction, and some goes this way, some goes this way. Since these two branches are in parallel, they're going to have identical voltage drops. Current comes back together here, and the total current of 3 amps go back to the battery. So answer on question 7 is C. We're looking at a combination or a mixed circuit. Let's go ahead and look at number 8. And again, 8 looks very much like 6 and 7, but once again, we have different numbers. So in this case, we have a total current coming out of the battery of 12 amps. 6 amps go through the first resistor. 4 amps go through the second resistor. 2 amps go through the third one. Notice that all the circuit elements have the same potential difference or voltage drop. Well, that should tell you that you're looking at something that's in parallel, identical voltage drops. Also note that the currents through all the resistors, they add up to be the total current. So those are all indicative that this is probably a parallel circuit, and the only one of these that's a true parallel circuit that's going to have one resistor on each branch, 3 different branches, is B. All right, now let's look at question 9. Again, same setup, slightly different values in our table. This time we have 4 amps coming out of the battery. 3 amps go through 1. 3 amps also go through 2. 1 amp goes through 3. The battery potential difference is 12. Notice it's 3 and 9 for 1 and 2. Those add up to be 12. And the value across resistor 3 is 12, the same as the battery. Well, you probably figure this out by elimination, that our answer has to be D. And again, current's going to come out of the battery. It's going to get here, and it's going to split from this junction. Some's going to go down the R1, R2 branch. Some's going to go through the R3 branch. Remember that the branch voltage drops have to be the same as the battery voltage drop in parallel. So both of these branches drop 12 volts. If you measure the voltage here and here, you would get 12. But if you measure the drop across this R2 resistor and this R1 resistor, those drops will add up to be 12. That's why we see this 3 plus 9 is 12 pattern. That's also why we see that those two resistors have the same current, because these two resistors are in series with each other. If 3 amps go through one of them, 3 amps also have to go through the other one. Only 1 amp goes through here, and that's true because apparently this resistor has a much higher resistance than either one of these put together. All right, that's multiple choice question 9. All right, here's multiple choice question number 9. 3 identical incandescent light bulbs are connected in the arrangement shown below. When the power is turned on with the switch on the bulb C branch left open, so notice that branch right now is open, how do the brightnesses of the bulbs compare? Well, first of all, if this branch is open, no current runs through this branch. That means that bulb C is off. So we know it's not going to have any brightness. If this branch is off, notice that this circuit only has one pathway. It's a series circuit. And since these are identical bulbs in a series circuit, they're going to get the same amount of current. They have the same amount of resistance. Remember that the brightness we can compare by comparing the amount of power dissipated. And the easiest way to do that when we're dealing with light bulbs is to use P equals I squared R. So since these are in series with each other, they're going to have identical currents. They're the same kind of light bulb, so they're going to have identical resistances. That means they're going to dissipate the same amount of power and therefore have the same brightness. So bulb A and bulb B are going to have the same brightness, and they're both going to be brighter than bulb C. So we're looking at answer D as the correct answer here. Now let's move on to question 10. So question 10, 3 identical incandescent light bulbs are connected in the arrangement shown below. What happens to the brightness of bulb A when the switch on the bulb C branch is closed? All right, so when we close this switch, this no longer is a series circuit. Now it's a mixed circuit. So when it becomes a mixed circuit, that's going to change the total resistance. Remember that when you add parallel branches to a circuit, you actually decrease the total or equivalent resistance of your circuit. So by turning on this branch, we've now added a pathway and we've decreased the total amount of resistance of the circuit. Because the amount of resistance is decreased, the amount of current going through the circuit is going to increase. Well, that means that more current is going to leave the battery. Well, all that current has to go through bulb A. So if more current goes through here, remember P equals I squared R. If the current here goes up, the resistance doesn't change, it's fixed. The power dissipated has to go up, and therefore the brightness has to go up. So our answer to multiple choice question 10 is B. Because we decrease the resistance of the circuit, we increase the current that ultimately ends up going through bulb A, and by increasing the current, we increase the power dissipated at bulb A, and therefore we increase the brightness at bulb A. So now let's look at question number 11. So again, same question, but this time instead of looking at bulb A, we're looking at bulb B. Once we close this switch, remember before we closed the switch, this was a series circuit, and all the current had to go through bulb B, around, back to the battery. So before, the current going through A was the same as the current going through B. When we close this switch though, when the current gets to this point, some of the current goes this way, some of the current goes through the bulb C branch. What that tells me is that the amount of current going through B after we close the switch is less than it was before we closed the switch. And since P equals I squared R, the amount of current going through bulb B is going to decrease. And because I decreases, P is going to decrease. And when the power dissipated decreases, the brightness becomes less or dimmer. So our answer here on question number 11 is going to be A. Now let's look at 12. Again, 3 identical incandescent bulbs are connected in the arrangement shown below. When the power is turned on with the switch on the bulb C branch closed, how do the brightnesses of the bulbs compare? So now this switch is closed. Remember, they're all identical bulbs. They all have the same R value. R is equal for all 3. So what's going to determine their brightness is the I. All of the current goes through this bulb, which means it's going to have more power. So A is going to be the brightest. Since they're identical bulbs, once the current gets here, half of it's going to go through this way and half of it's going to go through this way, which means that these two bulbs are going to have the same amount of current. So they're going to have equal brightnesses. So A is going to be the greatest, and it's going to be equal to the brightness of B and C. So we're looking here at answer C is our correct answer on multiple choice question 12. So here's multiple choice question 13. The potential difference across the battery in the circuit illustrated above is 30 volts. So we're looking at a combination or mixed circuit. By how much will the magnitude of the potential difference, maybe voltage drop, across R3 change when R2 is removed from the circuit and its branch is left open? All right, before we can do anything, we're going to have to figure out what the voltage drop is now. To do that, we're first going to find the resistance of the parallel portion of the circuit. Remember to do that. 1 over Rp equals 1 over the first resistor, 10, plus 1 over the second resistor, also 10. So 1 over Rp equals 2 over 10. We've got to flip both of these sides of this equation. We get Rp equals 10 over 2. Rp equals 5 ohms. So now we're going to think of this whole circled parallel portion of the circuit as if it were a series resistor hooked up with this 10 ohm resistance. And that'll give us a total or equivalent resistance of 15 ohms for the circuit. All right, now we're going to find the current. So we're going to say I equals V, 30 volt battery, over equivalent resistance, 15. We'll get 2 amps of current. So as it sits now, the 2 amps is going to flow from the positive terminal. It's all going to go through resistor 1. It's going to get to this junction right here. Since these two resistors are the same, R2 and R3, the current's going to split evenly. 1 amp's going to go this way, 1 amp's going to go this way. So to find the voltage drop across R3, we're going to use Ohm's law, solve for V. V equals IR. So we're going to have 1 amp going through 10 ohms of resistance. So we're going to have a voltage drop of 10 volts. And that's before we remove R2. All right, so now let's remove R2. So when R2 gets removed, this branch is no longer there, which means now there's only one pathway, this pathway. And that pathway is a series circuit. So let's find the total resistance of the series circuit. Remember to do that, you just add up the resistances of each resistor. So we get 20 ohms. We'll find the total current using I equals V, 30 volt battery, over R, 20 ohms. We end up with a total current of 1.5 amps. And now to find the voltage drop across R3, all 1.5 amps has to go through R1 and R3. So V equals I, 1.5 amps, times R, 10 ohms. So the voltage drop or potential difference across R3 after the switch is 15 volts. So before the switch, 10 volts. After the switch, 15 volts. So the voltage increased by 5, and that leaves our answer as B. All right, let's move on to multiple choice 14. It looks very similar to number 13. Same circuit. This time we want to know by how much will the magnitude of the current through R1 change when R2 is removed. Well, if we go back to our previous work, remember that before we removed the circuit, we had a total resistance of 15 ohms. So before we removed it, our total was 15 ohms. So we calculated the total current, I equals 30 volts over 15 ohms, and we got a total current of 2 amps. This question is asking us specifically about the current through R1. All the current from the circuit has to go through R1. So before the switch was made, we had 2 amps going through R1. After the switch was made, remember this branch wasn't there, and the total resistance was 10 plus 10, or 20. And the total current was I equals 30 volts divided by 20 ohms. So I was equal to 1.5 amps. So before the switch, 2 amps of current went through R1. After the switch, 1.5 amps goes through R1. Therefore, our answer is C. The magnitude of the current through R1 decreases by 0.5 amps. So let's move along to multiple choice question 15. So 15, again, we've got a mixed circuit and we want to know the current through R2. So we want to know the current through this branch. Again, before we can do anything, we need to find the equivalent resistance of the parallel part of the circuit. 1 over Rp equals 1 over the first resistance plus 1 over the second resistance. We get a common denominator of 6. So 1/3 is 2/6 plus 1/6. 1 over Rp equals 3 over 6. We've got to flip both sides of that and get Rp equals 6 over 3, or Rp equals 2 ohms. So again, we think of this as this whole parallel part of the circuit as one series resistor hooked in series with this 4 ohm resistor, and we add those up to get a total resistance for the circuit of 6 ohms. To find the total current, I equals V, the 12-volt battery, over R, the total resistance. We end up with a total current of 2 amps. Here we're looking for the current through R2, not the current through R1. So 2 amps come out of the battery. 2 amps go through here. 2 amps get to this point and they split. Here's the thing. If these two resistors had equal resistance, we would have gotten 1 amp going this way and 1 amp going this way. But they don't. More of the current is going to go toward the side with less resistance. Less of the current is going to go toward the side with more resistance. So that ought to tell you that the answer here is going to have to be C. But let's go ahead and calculate it. Before we can calculate the current through each branch, we really need to know the voltage drop across each branch. And the way we're going to calculate that voltage drop, remember, we're thinking of this as one resistor. And that one resistor has an equivalent resistance of, let's see, what was it? 2 ohms. So all the current has to go through the whole parallel portion. So to calculate the parallel voltage drop, we're going to take the total current of 2 amps times the resistance of the parallel part of the circuit, 2 ohms, and we get a voltage drop of 4 volts. That's the voltage drop across the whole parallel part of the circuit. It's also the voltage drop across each branch. So it'd be the drop across R2. It would be the drop across R3. So we're looking at R2. So if we want to know the current through R2, we're going to take the voltage drop across R2, 4 volts, divided by the resistance of R2, 3 ohms, and I is going to equal 4/3 of an amp. So our answer is C. Let's move on to multiple choice 16. So the diagram above illustrates a circuit which contains a battery of internal resistance 0.5 connected in series to a resistor of resistance 3.5 amps. If 5 amps of current flow through the circuit, what is the EMF of the battery? The EMF is essentially the theoretical voltage of the battery. It's what the voltage of the battery would be if you had the battery and it wasn't hooked up to a circuit, but you used a voltmeter to measure the voltage. To figure this out, we first of all need to find the total resistance of the circuit. So it's a series circuit. We've got one resistor, 3.5 ohms, but there's also some resistance in the battery of 0.5 amps, 0.5 ohms rather. So to find the total resistance, we simply add those up. So the total resistance is going to equal the 3.5 plus the 0.5. We're going to have a total resistance of 4 ohms. And then to find the theoretical EMF of the battery, we're going to just use Ohm's law, V equals IR. So we have a total of 5 amps, and we have a total resistance of 4 ohms. So we're going to get a battery voltage or EMF of 20 volts. So our answer on this one should be D. So let's move on to 16. 17 rather. So multiple choice 17 looks like the same question, but this time we want to know what is the potential difference across the terminals of the battery when the circuit is on. So when we talked about EMF, we were measuring the potential difference when the circuit was not on, when the battery was disconnected from the circuit. When we actually turn the circuit on, the potential difference across that battery is going to be a little bit less than the theoretical maximum EMF. And that's because there's some resistance in the battery. And some of the energy from that battery is lost to heat as the current flows through it. So what we need to do is calculate the voltage drop across the battery. And to do that, we're going to use V equals IR. We already calculated a minute ago the current. The current through the battery was 5 amps. That was given to us actually in the problem. And the resistance in the battery was 0.5 ohms. So that gave us 2.5 volts. That's the voltage drop across the battery. That's how much it drops as the current moves through that battery. Now remember, it was rated, we calculated in the last problem, as a 20 volt EMF battery. That's what the label would say, 20 volts. But we're saying that when we turn the circuit on, it actually drops this much. So we're going to go the EMF minus the drop, 20 minus 2.5, and we're going to end up with a actual potential difference of 17.5 volts. All right, so number 18, which of the following correctly describes the total potential difference around loop A? So here we have a complicated circuit. We've got loop A up top, loop B on the bottom. This is where we want to use Kirchhoff's loop rule. Kirchhoff's loop rule essentially says that all the potential drops and raises across a loop have to add up to be zero. It's another way of stating the law of conservation of energy. So let's just start off. We could pick any point to start at, but I'm going to start, say, right about point C. And notice the current, I2, through this branch is going this direction. So we're going to go through this resistor, R1, in the direction that current is actually flowing. When you go through a resistor in the direction that current's flowing, energy is lost. So to calculate that drop in voltage, we're going to get a negative number. And we know that V equals IR. And since we're going in the direction of current, we know it's going to be negative. So for this first resistor, it's going to be negative I2 times the resistance of that first resistor, which is 0.5. We're going to continue to go around the loop, and then we're going to get to R1. Again, notice the current through that branch is going in this direction. So we're going to go through it in the direction of current, normal current flow. So we're going to get a negative drop. So we're going to get negative. The current in that branch is I1 times the resistance of 6 ohms. Then we're going to get to the other resistor. Again, now the current's flowing this way, so we're going to go through it in the direction of normal current flow. So we're going to get minus I2, this should be I1 right here, times 2.5 ohms. And then we're going to go through the battery. And we're going through the battery from positive to negative. Sort of opposite of current flow. When you go from a battery to positive, from positive to negative, you get a voltage increase. And it's going to increase by the amount of the voltage of the battery, in this case, plus 18 volts. All those voltage drops and raises have to add up to be zero. So I know this is a little sloppy here, but if you look at what I've got, that's the same answer as answer A. So let's move on to 19. Which of the following correctly uses Kirchhoff's junction rule to describe the currents which enter and leave junction A? All right, here's junction A. Kirchhoff's junction rule is another way of stating the law of conservation of charge. And it essentially says that the currents entering a junction have to equal the sum of the currents leaving the junction. So if you look, we have current I1 is coming into junction A. So we're going to say I1. That's the only one coming in. Going out, we have I2 and I3. So that tells me that I1 has to equal to the sum of I2 and I3. Kirchhoff's junction rule. The currents entering a junction have to equal the sum of the currents exiting the junction. So our answer on this is going to be B. All right, then we get to the free response question. All right, so on the free response, in the three circuits shown above, the batteries are all identical and the light bulbs are all identical. In circuit 1, a single light bulb is connected to the battery. In circuits 2 and 3, 2 light bulbs are connected to the battery in different ways as shown. The light bulbs are labeled A through E. Part A, rank the magnitudes of the potential differences across light bulbs A, B, C, D, and E from largest to smallest. If any light bulbs have the same potential difference across them, state that explicitly. Briefly explain how you determined your ranking. First of all, this is just a series circuit with one bulb. We know that Kirchhoff's loop rule says the sum of the potential drops and raises across a loop has to equal to 0. So if we go through the battery, the voltage is going to increase by whatever the voltage of the battery is. Let's say it's a 12-volt battery. The only place it's going to drop is at A, which means the drop here has to be the same as the voltage here. Circuit 2 rather, is a series circuit with 2 light bulbs hooked in series with each other. If this were a 12-volt battery, the sum of the drops across B and C have to sum up to be 12. Since they're identical bulbs, this would be 6 volts and this would be 6 volts. Remember, if this were 12 over here, the drop here would have to be 12. All right, again, let's just assume this was a 12-volt battery. This is a parallel circuit, and you can tell because the bulbs are connected on both sides. Remember that in parallel, the voltage across each branch is the same as the voltage of the battery, which means the voltage drop across this one and this one are both 12. So if we're ranking these, A, D, and E all are going to be the same as the voltage of the battery. So we're going to say A is equal to D is equal to E, and those are greater than B, which is equal to C, because those are both equal to 6. And my description was pretty much what I went through to arrive at those questions. Make sure, though, that you explain how you got there. You could use numbers like I did here if you need to. Part B. The batteries all start with an identical amount of usable energy and are all connected to the light bulbs in circuits at the same time. In which circuit will the battery run out of usable energy first? All right, so the circuit that's going to run out of power first is going to be circuit 3. And the reason that's true is that in circuit 3, the bulbs are in parallel. Remember, when you add branches to a parallel circuit, the resistance decreases even below the resistance of each individual resistor. So circuit 3 is going to have the lowest resistance. Because it has the lowest resistance, it's going to have the most current. Remember that power equals I squared times R. So the circuit with the most current is going to dissipate the most power. Also remember that energy is equal to power times time. So the circuit that dissipates the most power is also going to run out of energy the fastest. So again, answer there, circuit 3, using the logic that circuit 3 has the least amount of resistance, therefore it's going to have the most current. Because it has the most current, it's going to dissipate the most power. And because energy is power times time, the circuit that dissipates the most power is also going to run out of energy first. And then the second one, in which circuit will the battery run out of usable energy last? Well, the answer to that question is that the one that's going to run out of energy last is going to be circuit 2. For the same reason we talked about with the one that runs out first. Circuit 2 is a series circuit. It's going to have more resistance than any of the other two circuits. Because it has more resistance, it's going to have less current. Because there's less current, it's going to dissipate less power. And because it dissipates less power, it's going to run out of energy more slowly. So again, our answer here, circuit 2. All right, I hope that helps. And that's the end of our circuit practice problems.